Patterson here. In this video, we're going to take a look at phase diagrams. Okay, first off, a phase diagram is a diagram that has temperature and pressure listed as parameters compared to states of matter. All right, so if we take a look at the x-axis on this graph, you have temperature in degrees Celsius here, and on the y-axis, you have pressure in atmospheres. And let's think about how those things affect the states of matter. Well, if you increase the temperature, you can go from a solid to a liquid to a gas. And if you decrease temperature, you can reverse that process. But what about pressure? All right, pressure does come into play there. Let's imagine that we have a gas and we put a lot of pressure on it. What that's going to do is force those particles really close to each other. When they get really close to each other, intermolecular forces can overtake. Can become great enough that the particles start to stick together. So we'll go from a gas to a liquid. Okay, so we got to consider both of those things whenever we talk about states of matter and what state of matter would be present at a set of given temperature, pressure conditions. Okay, so I've got a phase diagram here for water. So let's consider what this graph is telling us. Okay, so a couple of things you're going to notice here is you see three states of matter. So you have ice, which is solid. Okay, ice here. And then you have the liquid water right here, and then you have water vapor. All right. So I think it's easiest to start with a gas. Let's imagine what conditions we need for a gas. We need to have high temperature. All right, and we want the particles to be really spaced out, really far apart. So a low pressure, because remember, gases apply pressure to their surroundings by colliding with the walls. If we decrease those collisions, then the pressure goes down. So if we have very few collisions, we have low pressure, we have large particle spacing. So we want low pressure and high temperature. So where does that occur on the graph? Well, low pressure this way, high temperature this way. So we're going to find our gases over in this region. So let's consider a point here. Let's go right here. And that looks like it's going to be, I'm going to call it about, maybe 300 degrees Celsius. And I go over here on the x-axis or y-axis. That's a little over 1 atmosphere. So just a little bit greater pressure than what we experience normally. So at that temperature, we would know, hey, if we have water that is above 100 degrees Celsius at approximately 1 atmosphere, it's going to boil. It's going to turn into a gas. But what happens if we change the conditions? Okay, let's change the condition of pressure. All right, so instead of looking at this pressure here, let's really ramp it up and see what happens. If I stay at this same temperature, let's say it was 300, and if I go straight up, I can actually come across this boundary right here, this line, to a point, to an area, I should say, where I'm no longer in the gas phase. I'm in the liquid water phase. And that's going to occur at this really high temperature, or really high pressures. All right? So what's happening is the pressure applied to that keeps the particles close together so that even the increase in temperature won't separate the particles to turn into a gas. Okay, so we can look at different conditions and tell what state of matter would be present, but let's now look at how these phase diagrams are constructed and how to interpret them. All right, so you'll see this line here. There's a line that's here, line here, and going this way. How do we come up with those? Well, what is done to get those is you test varying pressures and temperatures of conditions and see what states of matter are present. Notice you have 3 different lines. It's not just one particular line. Okay, so along any of those lines right here, This is the boundary. This is the cutoff at what temperature and pressure you could have both water vapor, which is on the bottom side of the line, and solid ice, no liquid water. Along this section here, these are the pressure and temperature conditions where you could have water vapor and liquid water present at the exact same time. So let's look at room temperature. That's going to be somewhere around point C here. And we know at room temperature we can have water in the air. It could be humid, all right, and we could have liquid water. Both could exist at that temperature and pressure condition. All right. Now you can go up this way. Same thing here. These temperature and pressure conditions. That's where you have ice, solid ice, with liquid water present. But there is a particular, two particular points that we need to take a look at. So you can see right here we have a triple point. This is the pressure and temperature conditions where you could have three states of matter present at the exact same time. Down here, or up here, is the critical point. This is the pressure and temperature conditions at which you can't differentiate between water vapor and liquid water. The density of the vapor matches that of the liquid, so really there's no distinguishing between the two. Okay? So let's take a look at some of the points that I have on here, and let's consider them for just a moment. Let's look at point A. All right, so 1 atmosphere of pressure, a little under 1 atmosphere of pressure, and a temperature that is well below 0. So I can read that by looking at my X and Y axes. I would have solid ice present under those conditions. Okay, water would be solid ice. You would not have water vapor or liquid water present with those conditions. Okay, how about B? Well, that pressure and temperature conditions, temperature, I'm going to say it's close to room temperature or maybe just above, okay, room temperature there, and the pressure just above 1 atmosphere, so a little bit higher than what we normally experience. So we would have liquid water present. Okay, how about C? At point C here, now this is probably closer to room temperature here, and pressure, it's going to be pretty low. So a lot of that water is going to want to go into the vapor phase, the gaseous phase. Okay, but we could also have liquid water present. We can have, since we're on the line, we can have 2 states of matter present. Okay, so let's say you are given a set of conditions and you're asked to predict what state of matter would be present. Let's take a look at that. Let's say that we're at a skating rink and we're on our ice skates. There's an ice skating rink, and we have ice present. We're skating across it, and it's below the freezing mark. Let's say it's at this temperature. Okay, so at atmospheric pressure, which is 1 atmosphere, it's going to be solid ice. But what happens to it when we stand on it with our skates? The skates have a very narrow area on the blade. We put our weight down on it. That puts a lot of pressure on that ice. When we increase the pressure, watch what happens. If we consider the same temperature but increase the pressure, we're going to end up here. So the state of matter that would be present would be water. And this is why you glide across frozen ice on ice skates so easily. What you're doing is you're creating a layer of water between the ice and your skates and using it as a lubricant to slide across the surface. Okay, so hopefully you learned a little bit about phase diagrams here. Okay, and we'll get some practice with interpreting these a little bit more in the next assignment.